Imagine a hotel with an infinite number of rooms. Even if every room is occupied, this infinite hotel can always accommodate more guests. By shifting the person in room n to room n+1, we create an empty first room without losing anyone. This reveals the core property of countable infinity, or Aleph null. It is a set that can be put into a one-to-one correspondence with a proper subset of itself. To compare these infinite sizes rigorously, we use cardinality. Rather than counting, we seek a bijection, a perfect pairing where every item in one set has exactly one partner in the other. If such a mapping exists, the sets are the same size, regardless of how much larger one might appear at first glance. Take the integers, for example. They seem twice as large as the natural numbers because they extend infinitely in both directions. However, by alternating between positive and negative values in a single list, we can pair every integer with a natural number. This proves that the set of all integers still has the cardinality of Aleph null. Rational numbers, the fractions, are even denser, filling every gap between integers. Yet, by arranging them in a grid and weaving through them diagonally, we can still list them one by one. This snaking path ensures we hit every possible fraction, proving that even the dense rationals are no larger than the counting numbers. But does every infinity eventually fit into a list? When we look at the real numbers on a line, the texture of infinity changes. Unlike the discrete steps of integers or the gaps between fractions, the real numbers are a continuum. This shimmering density leads to a startling realization. There is no way to jump from one real number to the next, suggesting this infinity might be fundamentally different. To prove the real numbers are truly larger, we use a proof by contradiction. Suppose we actually could list every decimal between 0 and 1. By focusing on the diagonal digits of this hypothetical list, we can construct a new number that is guaranteed to differ from every single entry in at least one decimal place. This is Cantor's diagonal argument. Because our new number x differs from the first number at the first digit, the second at the second, and so on, it cannot exist anywhere on our complete list. This contradiction proves that the real numbers are uncountably infinite, a magnitude of infinity strictly greater than Aleph null. This higher magnitude is the cardinality of the power set, the collection of all possible subsets of the natural numbers. Just as we couldn't list the reals, we can never list every possible combination of integers. This creates a jump from the countable Aleph null to the size of the continuum. Cantor's theorem proves that the power set of any set always has a strictly larger cardinality than the set itself. This discovery implies an infinite staircase of infinities, where we can always build a larger set by looking at the collection of its own subsets. We now face a gap. Is there an infinity larger than the counting numbers, but smaller than the continuum? The Continuum Hypothesis proposes that the answer is no, that the continuum is the very next level, Aleph 1. To solve this, we must look at the rules of mathematics itself. The ZFC axioms are the foundational rules we use to build sets. They act as the logic gates for what is mathematically possible. However, within these standard rules, the size of the continuum remains an elusive mystery that the axioms themselves cannot fully settle. In 1938, Kurt Gödel showed that it is impossible to disprove the continuum hypothesis using our standard axioms. He constructed a mathematical universe where the hypothesis is true, proving that assuming the continuum is the next size of infinity doesn't lead to any contradictions. Later, Gödel Cohen proved the opposite. You can also build a consistent universe where the continuum hypothesis is false. He developed a technique called forcing to show that the continuum could be much larger than Aleph 1 without breaking the rules of ZFC. This means the continuum hypothesis is independent of our axioms. Like a parallel line in geometry, it can be either true or false depending on the universe you choose to work in. Our foundational logic is simply not powerful enough to determine the ultimate structure of the infinite. This independence reveals a profound truth. Mathematical reality is larger than our ability to describe it. We are left with a landscape of infinite possibilities, where the hierarchy of sizes transcends simple certainty, reminding us that the reach of human logic is still growing.